All right, good morning, ladies and gentlemen. Today we are going to discuss or continue our discussion on errors, type 1, type 2. We're going to specifically get in today on how to calculate the probability of a type 2 error and also what are the implications of making a type 1 or a type 2 error. I want to stress that there are some, pretty technical discussions that we'll have today, and if you haven't done the textbook reading and you haven't seen the other two videos, I strongly suggest doing that before moving on to this video, because I'm going to assume some knowledge and I'm going to move pretty quickly through certain things. Okay. Of course, as always, you can join me during our SGI session daily, and you can ask whatever questions you might have there. So before we get started, I want you to think about the do now for a little bit. So take a moment and pause the video, come back when you're ready. Okay, so assuming you paused and thought about the do now, let's get into a discussion. So how do you think we can reduce the probability of a type 2 error without increasing the probability of a type 1 error? Well, a common thought is, well, let's see, if I want to reduce the probability of a type 2 error, one thing I can do is adjust alpha. And because we discussed that a type 2 error is, let's see if I can draw a diagram so the probability of a type 2 error is if we live in the world where H null is false, and we go ahead and we establish a rejection region based on alpha. Okay. Anything that lies to the left of this vertical line that I just drew, again, remember, we're in the world where H null is false. So really, the true distribution is centered at whatever the true parameter is. Anything that falls to the left of this vertical line will lead us to fail to reject H null. But if H null is false, then that's bad. So if anything lands within the region that I just pointed to, this is a type 2 error. So forgot how to change. Okay, let me just change the color. So this blue region here, that area represents the probability of a type 2 error. Please excuse my handwriting, but this is a probability of a type 2 error. And you can clearly see that it very much depends on where that vertical line is placed. So if I increase alpha, let's say make it 0.1, well, that vertical line is going to shift left, right? Because I'm correct, so that vertical line is going to shift left, correct? The reason is that if alpha is 0.1, then the rejection region area increases. So that vertical line is going to have to shift left in order to create more area in that uppermost tail. So if I shift that vertical line left, then that blue area will, as a result, shrink. So we've reduced the probability of a type 2 error, but at the same time, we've increased the probability of a type 1 error. You might recall from previous videos that the probability of a type 1 error is exactly equal to alpha. All right. So while that helps us out in the type 2 world, it hurts us in the type 1 world. So we want another solution. And we're going to discuss that other solution momentarily. Before we move on, I want to introduce some vocab and notation that you're going to need for today. So I'm going to be using this term, and I introduced it in the previous videos too, but just so we're clear now, this term p hat star. So this is the sample statistic on the very edge of the rejection region. So in the example that I just drew, P hat star would be right over here. Okay, and it is determined based on the null hypothesized distribution. Because remember, when we're running a hypothesis test, that is the distribution that we think is true. So everything with regards to the rejection region is going to be determined based on that distribution. Okay, so p hat star is the sample statistic on the very edge of the rejection region. P hat star is related to Z star, and I stress that because a few people asked me, why not use Z star? They're related. I want to use P hat star in this case because we are dealing with the sampling distribution of proportions, two different sampling distributions of proportions, and so I don't want to convert them both to a standard normal model. So we're going to use P hat star rather than Z star, but they are related. So P hat star has a Z score of Z star. Z star, if you recall, that's the critical value we discussed in class when we last met. And of course, the critical value is the Z score of that statistic that exists right on the edge of the rejection region. Okay, all right. So back to the do now. How do you think we can reduce the probability of a type 2 error without increasing the probability of a type 1 error? So adjusting alpha is not going to work, as we saw. The other option that hopefully you came to is to increase the sample size. So if we increase the sample size, there's an effect on the sampling distribution that makes the sampling distribution essentially tighter around the center. And what do I mean by that? Well, remember, if we have a larger sample size, then any individual sample has a better chance of being a closer estimate to the parameter, right? So if we're drawing samples of a very large size, then all of our samples are going to be, or we have a higher probability that our samples are going to be closer to the true parameter. And so as a result, I'll show you an example here. So here you can see a normal distribution, okay? Right now, over here, you can see that the sample size is 132. Let's see what happens when I increase sample size. Notice that the normal distribution, or the distribution of sample proportions, it's becoming a lot tighter around the center of that distribution. It's peaking around the value P, and the tails are shrinking. The tails are becoming a lot lower on the vertical axis. So I'll show that one more time. So right now I'm reducing n. Notice n is now around 27. You can see on the left side of the screen. And as a result, our sampling distribution is a little bit lower, has more pronounced tails. As I increase n, now this is a distribution of sample proportions with higher sample size, meaning that each one of our individual samples has a better chance of estimating the true parameter. And that's why many more of our samples are centered around the true parameter, which of course is right over here, which is P. Right now I have it set to be 0.3. All right, so why is this happening? Well, the mathematics of the situation is that, of course, increasing sample size reduces our standard error. So we're using examples dealing with sampling distributions of sample proportions, but the same can be said for sampling distributions of sample means. Here are your formulas: standard error for sample proportions, radical PQ over N, and you might recall standard error for sample means is sigma over radical N. That N being in the denominator means that if we increase the sample size, then the overall fraction value is going to decrease. In other words, the standard error will decrease. And that's why you're seeing when n increases, the distribution itself becomes more tight around the center. Okay, and I have a reminder for me to see Desmos, but we already did that, so we will go back to Desmos again. All right, so anyway, to finish, the best way to reduce the probability of a type 2 error without increasing the probability of a type 1 error is to increase the sample size. Now, you might be wondering why exactly that is, and hopefully what I'm about to show you helps with your understanding. So we're going to go back to this Desmos. So let's go back to like a more reasonable sample size just for illustration purposes. So let's say this is our null distribution, right? Right now, we're based on maybe whatever we've been noticing, we're assuming that P is distributed, that P, the population parameter, is 0.3. That's our null hypothesis. For simplicity's sake, again, we're going to be doing an upper tail test, okay? And that'll come into play in just a moment. But right now, we are assuming that the true parameter is equal to 0.3. And so this distribution is based off of that null assumption. Let me see if I can annotate. All right, I want to draw. Let's see. All right, so this is a red curve. So our red curve is assuming all conditions are met. We're distributed normally with a center of 0.3. And if you do, well, actually, let's go ahead and just write the formula because I don't know the standard error off the top of my head. But to calculate this standard error, we would use 0.3 times 0.7 all over 90, which is our current n. All right, so that's what's currently going on. But let's just say we live in a world where H null is actually false. That means somewhere out there, there exists the true sampling distribution. All right, that is going to be this curve right here. Let's say that it turns out that the true parameter is actually 0.42. Okay, now look, you have to understand in practice, this wouldn't actually happen. We wouldn't actually know what the true parameter is equal to, but this is just for an illustration purpose, okay? So we're in the world where H null is false, right? Because we're discussing a type 2 error. So H null is false, which means that somewhere out there, there exists a true sampling distribution. And that's the black curve that you're seeing there. So let me just be clear. This is based off of the, didn't mean to do that. I want to draw. This distribution that you see here is based off of the null hypothesis. Okay, and the black distribution, this is actually based off of what is true. So again, assuming all conditions are met when we select our samples, the black distribution will be centered at 0.42, and it will have a standard deviation of 0.42 times 0.58 all over, again, 90. And this is the true distribution. Okay. Now, what would cause us to fail to reject H null? Because as we have the benefit of knowing today that H null is actually false, what would cause us to fail to reject H null? Well, of course, if we obtain a sample that's in the rejection region. So let's say that, again, for simplicity's sake, alpha is equal to 0.05. And let me draw that. And I'll use yellow for alpha. So we're going to just say that alpha, actually, no, we'll use purple. So alpha is going to equal 0.05. Well, how am I going to determine the rejection region? Well, of course, the rejection region, I'm going to completely ignore the true distribution. The rejection region depends entirely on the null hypothesized distribution, right? Every time you run a hypothesis test, you use the null distribution to calculate the rejection region. And then from there, we go ahead, obtain our sample, calculate a p-value, and see if that obtained sample lies within the rejection region. Or in other words, does the p-value, is it less than alpha or is it greater than alpha? So our rejection region, since it's an upper tail test, is going to be the top 5% of this distribution. So I went ahead and now things are going to slow down a little bit because this calculation is, I guess, intense for the computer. But in a moment, there should be, that purple vertical line. That purple vertical line is the rejection region. So let me use red. So if we, as the researchers, obtain a sample to the right of this vertical line, then we are going to reject the null hypothesis. However, if we obtain a sample to the left of this vertical line, then we will fail to reject the null hypothesis. Of course, the p-hat value that is at the very edge of this rejection region, that's going to be called p-hat star. So I'm just going to label it over here. P-hat star is this x value that this vertical line crosses through. All right, anything to the left of p-hat star, we will fail to reject H null. Anything to the right, we will reject H null. Now remember, let's go back to mouse. Remember, there is actually a true distribution out here, okay? And that is this black distribution. So ignoring the area, let me erase actually. Ignoring that area, because now when it comes down to it, the area we're actually interested in is the area to the left of the vertical line, based off of now the true distribution, because in reality, our samples are coming from that true distribution. So once I establish p-hat star, I can actually just ignore the hypothetical distribution. All that is good for is determining the location of the rejection region from our point of view as researchers. But again, remember, really what's generating our distribution is what's generating our samples is this true distribution, the black one. All right, so in order to calculate the probability of a type 2 error, we want to know what is the probability. And I'm going to use black here because we're using the black distribution. My mistake, let me readjust. We're using the black distribution to generate our samples. And so we're going to ask the question, based on the black distribution, the true distribution, what is the probability of obtaining a p-hat that is less than or equal to that value p-hat star? And let me go ahead and write p-hat star as a purple symbol. Okay, that's the probability of a type 2 error. And of course, we refer to that as beta. Okay, so that area to the left of the vertical line, based off of the true distribution, is a type 2 error, and that's what we call beta, that means that the probability of obtaining a powerful result, so the probability of power, is going to be anything to the right of that vertical line. So the probability of power is just going to equal 1 minus beta. And again, we're calculating these probabilities based off of the true distribution because we are in a world where H null is false. So in practice, from the researcher's perspective, they don't know that H null is false, so they'll calculate their rejection region based off of H null. And then behind the scenes, again, this is a number that is not calculated in practice, but behind the scenes, the power of the test is calculated by finding the probability of obtaining a sample that is to the right of p hat star, or it would be, let's just leave it at that. The probability of a powerful test, a powerful result, is the probability of obtaining a sample, in this case, to the right of p hat star. Again, I want to reiterate that this is based off of doing an upper tail test. You can do a similar logical argument for a lower tail test or even a two-tail test. I will leave that up to you. Really, I want you to leave today by understanding the concept behind, all of these calculations. All right, now now that we have all that out of the way, back to the do now. Let's see what happens when we increase the sample size. So I'm actually going to go ahead and erase all of this. So we're back to hypotheticals. But I want you to just keep in mind everything we just discussed when seeing what happens when we adjust our sample size. So a little bit of a delay while I erase all this stuff. Actually, I wish I kept that. Yeah, let's keep this. All right. Okay. Sorry, folks. I'm not a professional, as you, I'm sure, are well aware of. All right. So now let's see what happens. Let's go back to the null hypothesized distribution. Okay. Because remember, it is the null hypothesized distribution that entirely tells us where p hat star is located. Now, if I leave alpha alone, alpha is still 0.05. Let's see what happens when I increase the sample size. Notice what happens to the vertical line. Now, there's going to be a significant delay, but ultimately, when all the calculations are done, notice what happens to the vertical line. Increasing sample size. I went from 90 to 410. All right, again, there's going to be a delay. Boom. And there you have it. So notice that that purple vertical line shifted pretty far to the left. And that's because alpha is still 0.05, but since our distribution has now smaller tails due to the increased sample size, that p hat star has to move further to the left or closer to the center in order to get a full 5%. If p hat star was where it was before, then let me see if I can draw this in to just show you where p hat star was before. It was somewhere around here. You'll notice that to the right of that drawn vertical line is nowhere near 5%. So in order to obtain 5% of rejection region, when we increase sample size, p hat star has to move closer to the center. Now, what does this mean? Well, let's see when we bring in the true distribution, you'll notice that this probability, the area to the left of that vertical purple line, when we're looking at it with respect to the black curve, which is the true distribution, you'll notice that area is a lot lower than what it was before. And if you don't believe me, just kind of rewind the video, see what the area to the left of the black curve was before we changed the sample size. So increasing the sample size reduced the probability of a type 2 error. It increased the power of the test. All at the same time, it did not change whatsoever the probability of a type 1 error because alpha was locked in at 0.05. So this is an important takeaway. Increasing sample size does not at all affect a type 1 error. It stays, the type 1 error probability stays exactly the same. All right, so that's key. All right, so I think that discussion is, let me get rid of all of my annotations. I can't do that, I guess. Technical difficulties, clear maybe? Yeah, okay. Okay, so hopefully that made sense. We're gonna kind of move on in the discussion. Again, any lingering questions, please feel free to come to the meeting today, tomorrow, whenever. Moving on. Does increasing sample size decrease probability of type 1 error? That's what we just discussed. And again, the answer is no. Remember, all increasing sample size does is it makes your distribution a little bit tighter around the center. And yes, that will change the location of p hat star, but alpha is still 0.05. So the rejection region is still 5% of the distribution, no matter what it looks like. All right, I'd like you to take a moment and determine the probability of a type 2 error based on this situation. So go ahead, pause the video, try it out, and see what you can do. And I am going to pause myself. Okay, I'm back. I just wanted to do some of the calculations off screen. So in this situation, we're looking for the probability of a type 1 error. We're running a hypothesis test. We're assuming that p equals 0.3. This is an upper tail test. And sample size of 81, alpha 0.05. Now, assuming all the sample selections were done appropriately, then our hypothesized distribution will be distributed normally. So this is the hypothesized distribution, going back to red for the hypothesized distribution. And if all conditions are met, we will have a sampling distribution that's centered, that's normal, centered at 0.3 with a standard error of 0.0509. That standard error was radical 0.3 times 0.7 over n, over 81. All right, from there I calculated p hat star. So that p hat star is just the 95th percentile of this distribution. I'm not going to tell you how to do that. That's something that you can kind of figure out on your own. So think about it. Again, if you have questions, come to SGI. All right. Now, it turns out that somehow the truth comes out that P is actually equal to 0.42. All right. So realistically, the true distribution of sample proportions, sorry, something seems to be freezing. Okay, there we go. The true distribution of sample proportions is actually centered at 0.42 with a standard error of 0.0548. All right, so drawing that distribution, I'm going to do the best I can to kind of draw it down here. Again, remember they do overlap as you saw in Desmos, but it's a little easier to see it this way when we're calculating our probability. So really what we're interested in for type 2 error is everything to the left of this vertical line. So I'm going to set up the equation that says, what is the probability of obtaining a p hat from this black distribution, which is less than or equal to 0.3837. Okay, and I'm going to go ahead and calculate that real quick. I'm not going to tell you again, I'm not going to tell you how to do it. This is something I want you to think about, but I will give you the number. That way you can check your answer. And if you don't know, 0.2539. If you're not sure how I got that, again, come to SGI. So in this case, the probability of a type 2 error is 0.2538. I said, actually it is a 9, but I wrote an 8. All right. Which means that the probability of a powerful result would be 1 minus that, which is 0.7461. So we actually have a pretty decent shot at correctly rejecting H null here. All right. That is that discussion. So that's basically walking you through the idea of probability of a type 1, probability of a type 2 error. Any further questions, please come to SGI, ask them. If there's something that I didn't discuss clearly, let me know and maybe I can make a follow-up video. But for now, we're going to move on and take a look at this problem. So read through it, and I would like you to take a few moments to write down some responses. I'm going to pause myself here, and you should pause as well. I'll be back momentarily. All right, folks, welcome back. Before we discuss the solutions to these problems, a quick word from our sponsor, Couch Potato Brand Snacks. Can't go outside? Grab some packs of these snacks. Okay, folks, that's Couch Potato Brand Snacks. So we have a, quarantine going on. So, hey, grab some of those snacks. All right, back to the problem at hand. We're looking to state the null and alternative hypotheses. Of course, the null hypothesis would be that P is equal to 0.1, right? We can't, we have to assume that the person or the company is telling the truth, and it's up to, in this case, a consumer advocacy group to provide the evidence that shows that maybe the businessman is lying, or the business is lying, the company is lying. So it's up to the consumer advocacy group to prove or provide evidence, at least, that shows that the company is lying. So that's why our null hypothesis is going to be that P is equal to 0.1, and that's what we will assume throughout the entire hypothesis test. And the alternative is that P is actually greater than 0.1. 2 I left blank because this is really just sort of a discussion and sort of a hypothetical, like what might happen. So a type 1 error, well, what that means is that the company is actually telling the truth, but we end up rejecting H null anyway. And so now this consumer advocacy group tells the world that, hey, these flares are actually defective a lot more frequently than are being reported. And then this could cause people to go ahead and maybe sue that company or something along those lines, or bad press. And, maybe this company goes out of business. All right. So it could lead to like pretty devastating effects for this company and whoever maybe works there. Right. So we definitely don't want that to happen. We don't want a type 1 error to occur. On the same token, we don't really want a type 2 error to occur either, because in this context, the type 2 error means that H null is false, but we fail to reject it. So this company is maybe passing off some faulty flares, but we don't catch it. And nothing happens except that this company continues to sell more faulty flares. And who knows, maybe in an emergency situation, someone has has a faulty flare and it doesn't go off when it's needed. Okay, so, and that can also lead to devastating results. So the point is, depending on the situation, type 1 errors could be really bad, and type 2 errors could also be really bad. So we want to minimize the effect of both of these things wherever possible. Now, it is impossible to completely remove them, and so that's why I said, that's why there's sort of like this little dance between these probabilities, trying to minimize one while not affecting the other. And so really the two major things that we can do as statisticians is adjust alpha and to something reasonable, right? We can't push it off to 0. It's got to be something reasonable. And at the same time, we could also make sure that we get as large a sample size as possible while still making sure that, it's an appropriate sample, it's a random sample, all those things. All right. And so moving on, question 3 says, what is the probability that we incorrectly claim that the true proportion of defective flares is higher than 0.1? So what they're describing there is a type 1 error. What's the probability of that? And of course, we know from previous discussions that the probability of a type 1 error is just simply 0.05. So how do we reduce this probability? Well, we just simply change alpha to 0.01, and there we have it. But as you know, that will also now increase the probability of a type 2 error. So once again, there's that balance. Okay, so just some things to think about. All right, so that's all. I'm going to scroll now to the classwork/homework. This is going to be due on, let's see, probably, I guess, Thursday. Yeah, Thursday. What's today's date? Today's the 24th. So Thursday, the 26th, this will be due. I'll type this up. All right, just make sure I didn't have anything else below this, but I'll type this up and I'll post the worksheet. And once again, if there are any questions, please come to SGI. And I just hope everyone's doing okay. And I know this is a long video, but hey, you're able to fast forward and all that stuff. All right, ladies and gentlemen, please be well and talk to you soon.